Okay, so we're doing gases. You guys say hello to all the slackers who aren't here today. Here, let me show you. There you go. Oh, it's dark. You are creatures of the dark. Can you see yourself up there yet? No, look how dark that is. I see nothing. Sorry. Speak the words, say hello. They don't want to talk to you people. You should be here. Okay, so we're looking at gases, and we already did a little bit of Avogadro's law, and it's just showing the relationship between volume and number of moles. We did Boyle's law, which focused on pressure and volume. So again, they're just looking at distinct qualities two at a time, typically, that's on there. The next one is Charles' law, and Charles' law over here relates volume and temperature. Is this big enough for you guys to see, or does it need to be bigger? Bigger? Okay. Relates volume and temperature. So in this case, pressure and number of moles remains constant. So remember that N is number of moles. So in this case, your equation looks like V1 over T1 equals V2 over T2. And I'm going to kind of block this off a little bit because that didn't use much space, and I need more space for the other stuff. Okay, so I'm doing these in different colors. It just helps, it makes it a little bit easier to keep up with this stuff here. The next one is Dalton's law of partial pressure, which is really easy. And if you'll take out your green pages, you guys take out your green pages, I think Dalton's law of partial pressure is on here. So remember to look at the little units that they have here. So we have atomic structure, equilibrium, kinetics, and remember over here on the right hand side are just the variables. On the back side of that, here are the gases and liquids. So learn to use this and not waste time when you're on that multiple choice section hunting stuff down. So we're looking at gases here. Dalton's law of partial pressure is this one right here. The total pressure is equal to the pressure of the first gas plus the pressure of the second gas plus the pressure of the third gas, and so on. So Dalton's law of partial pressure is really simple, and you don't have to memorize the equation. So the total pressure is equal to the pressure of the first gas plus the pressure of the second gas plus the pressure of however many gases there are on this. And a lot of times, instead of putting 1, 2, and 3, they might put the pressure of the O2 plus the pressure of the HE plus the pressure of the nitrogen gas. So they might put it like that instead of just 1s, 2s, and 3s. So you get some different ways of looking at this. And if you guys want to move up a little bit closer, since this is kind of wonky up here, you're welcome to do that. So when we have Dalton's law of partial pressure, what it's saying is, in a mix of gases, the total pressure is the sum of all the partial pressures. The total pressure is the sum of all the partial pressures. So when we have multitudes of gases in the atmosphere, the pressure of the oxygen in the atmosphere plus the pressure of the nitrogen gas in the atmosphere, they're not the same pressures. Yeah, because the pressures depend on the volume and the temperature, and they're not the same amounts, right? So we have those pressures that are different, and so to get the total overall pressure, like the air pressure today, we would have to add up all those pressures together. Okay, here's a big key, and I'm going to put this in a box. Use this, and we're going to do this lab next week. Use this when you collect a gas over water, which is the basic way to collect a gas. Because it keeps it contained. So you're going to use this Dalton's law of partial pressure always, always, always when you collect a gas over water. So let me explain that. So when we run an experiment, let's say we do an experiment in a test tube and we know it's going to produce a gas, right? We know it's going to. We can catch that gas and we can figure out how much is made. all we have to do is put a test tube on it. We put it in run the whole thing in a test tube, put a stopper in it with a hole, and we have glass tubes that we can stick in there, and we can direct the gas to be caught into another test tube. And you typically do that by running it through water. So let me make a lovely sketch of that. So here we have a test tube, and you have your stuff going up here and it's making gas, right? And you have a stopper in here, and there's a hole in the stopper. And you direct that into this pan of water. My, what a lovely drawing you're making, Miss Howard. Into something that goes like this, and you catch it in another test tube. Typically what we're going to do is we're going to catch it in something called a eudiometer. So this one has water all the way up to here, and what happens is the gas bubbles up through here and it displaces the water, pushes the water down, and this thing fills up with gas. Yes? So we can actually run an experiment. Here we go. We run the experiment in here and we catch the gas that's produced. We catch the gas and we direct it in here and we run it through water. Now, why are we using Dalton's law of partial pressure? Because some of the gas that's in here is not the gas just from this, it's also some water vapor. So in order to get the pressure, so we can, remember if we have PV equals nRT, we can get the temperature of the water. We're going to use that. We can get the volume, because if we use a eudiometer is like it's like a big long test tube that's graduated, like a graduated cylinder, only it's about 2 feet long. And you collect stuff in it like this, and it'll displace the water. But you catch it in there. We can get the volume, we can get the temperature, we can get the pressure. All we have to do is find the pressure in the atmosphere today, and then we use the water pressure over here, take that out, and then from that we can get number of moles. So from this, we can find the number of moles of gas produced. You know, it's one thing to have it on paper and calculate what it should be, right? Because we could do that. We could go from, hey, here's the moles of the reactants, and I can find moles of product, but that's not reality. In reality, we never get that, right? There's always going to be some mess up there. So we can find the actual. Instead of just the theoretical, we can find the actual amount that we made. So what we do then is we take the total pressure. Typically, that's going to be the atmospheric pressure that you're at. And we have the whatever gas it is that we've collected here, plus the pressure of the water vapor that's in there, because it won't just be this gas, it's going to be water vapor. So what we end up doing is we have the total pressure. We can find it online. Yeah, I can go to weatherbug.com and find the pressure in Borger, Texas today. We have the pressure of water. What we have to do here is we look on a chart. There's a chart and it says at this temperature, the pressure of water is this. At this temperature, here's another pressure for water. So this is how we do this. And we basically, we have this number, we have this number. How do we find this one? Yeah, we just subtract, right? That's one of the biggest uses that we'll find for Dalton's law of partial pressure. So practically, and what we'll do next week is we'll use this to find the number of moles of a gas that we collect over water. So when you collect it over water, one of these pressures that you have here will be water vapor. And you have to deal with that and get it out of the way. So when we deal with all of these things right here, there are certain characteristics and certain rules that have to be followed. So the first one is that your temperature must be in Kelvin. That's a big, big deal. Your temperature has to be in Kelvin. That would be your Celsius plus 273, right? And the reason we do Kelvin is because there are no negative numbers. You throw in a negative number, which it's obvious, temperature can be negative, no problem at all. You throw in a negative number and it completely throws off your stuff. Because can you have negative moles? Can you have negative grams of stuff? No, you can't. So your temperature has to be in Kelvin. That's a big, big deal. And the pressure you have to choose whatever pressure unit you're going to use, and you have to be consistent. So you've got to be consistent about that. So it doesn't matter really which pressure unit you use. What matters is that you're consistent and you're using the same one throughout. That's a big deal. Okay? I personally like using atmospheres because standard pressure is one atmosphere. And so it's always easy when you're doing atmospheres, just, hey, it's standard pressure, it's times 1. So it makes your calculations easier. Now, there are a couple of other things on here, and the first one that's going to be weird that we didn't talk about in regular chemistry or first year chemistry is a mole fraction. So XA is mole fraction. And it's the mole fraction of a gas. And the reason this is important, I'm going to refer back to your green pages. The reason this is important, look right here. We have the pressure of the gas, we have the total pressure, and then we have this mole fraction thing, right? So this is another way to find moles. The whole thing is, ultimately, when you get stuck on a problem, you want to find moles, right? And then right beside it, here is what XA is. It's the moles of that gas divided by the total number of moles. It's kind of like a percent composition, right? Yeah, only it's in terms of moles. It's not percent, it's in terms of moles. This is really, really helpful. So it's saying, hey, this is how many moles of this particular gas, because usually we have a mixture of gases, right? It's hard not to have it's hard just to have a really pure gas. You have these mixtures. So here's the total pressure. Every time we use the pressure of the atmosphere on a day like this, it's a mixture of gases. So here's the total pressure. Here's the only gas we're concerned with. And then we have a mole fraction we can use. So from that, we can use this to get moles of that gas that's formed. So it's another way to find moles of something. So that's what the mole fraction is good for. And we'll do some problems with that. The next thing on here, with the mole fraction here, just what it is, here's the equation. I'm going to have you write it again here. Mole fraction is equal to the moles of gas A divided by the total moles of gases. And notice it's gases plural, right? That's going to be your moles of A. We're only concerned about that one gas. So we don't care about the moles of other crap. It's just the one gas. And I can guarantee you on the AP test, they're not going to give you just one gas. They're going to put all the other crap that's in there. Now right alongside this is going to be that mole fraction used in the equation with the partial pressures. So the pressure total times the mole fraction. And generally they're asking you to find this. That's usually what you want to look for. Because you can get the pressure of A. Okay, so and here's the deal. You might use, and it seems almost redundant, you might use this equation to get the pressure of, let's say this one is gas A, to get the pressure of the first gas, and then you take that and you're going to use the total pressure again and that pressure you just found, and now you're going to find the moles from that. So it's a pretty simple way, and they've got these right here together. So you've got this little equation here and here together that you can do that with. Now, the one other thing I'm going to throw in there, and it's not an equation, this is the partial pressure. The partial pressure is just the pressure of each gas in a mixture. And the reason this is important is because, you know, unless you're doing things in a vacuum where you're actually really focused on what gases are there, it's going to be a mixture. And think about this. If you have two gases that react, unless you have the exact amount and everything is perfect like you would have it on paper, then you're going to have three gases at the end. Let's say you've got two gases and they chemically react to form a third one. You're going to have some leftover stuff. And so what you have in the container is not just one gas, it's a combination of those gases. Okay, I'm going to stop the video here. This will be our second video so that I can actually load this.